this lecture we will learn about conditional probability and conditional expectation. Okay, these are two important tools which we will require for the analysis of many randomized algorithms. So, we will start with an example. Let us say we consider a population with n people, out of which let us say n f are females. This is the number of women, and let us say n c is the number of color blind people. Okay. So, we have two events, females and color blind people. We are randomly choosing some person from this group of n people, and when we say randomly, each person is equally likely to be chosen. So, when we do this, the events that we were interested in are NF and NC. NF, I mean, or rather the events are F and C. F denotes the event that the randomly chosen person is a female, and C denotes the event that the randomly chosen person is color blind. Clearly, the probability of F is equal to NF divided by the total number of people, and the probability of C is going to be equal to NC by N. Now, when we talk about conditional probability, what we are interested in is the event that the person is color blind. There is a conditioning on a particular event. So, let us just say, suppose we are told that the randomly chosen person is a female. Now, what is the probability that the person was color blind? So, we are interested in the probability that a randomly chosen person is color blind given that a female has been chosen. Okay, so, someone has made a choice and it has been told to you that the person who was picked was a female. Now, you are asked what is the probability that the person is color blind. So, if you look at our sample space, this is a set of females and this is a set of color blind people. They could have an intersection, they may not have an intersection, but this is the general diagram. Now, if we are told that the person is a female, then the probability that they are color blind is essentially the size of this region divided by the region of females. In other words, that is going to be, so this probability, if we denote, we will give a notation for that, we will denote it by probability C given F. Okay, we have introduced a notation, but the notion behind is essentially the same. We are interested in computing a probability, but we are restricting the sample space. Instead of considering the entire sample space, now we are restricting to the sample space which consists of only females. So, this probability should essentially be number of color blind females divided by number of females. It is a fraction of color blind people amongst women, that will be this probability. So, the probability of C given F is nothing but number of color blind females by number of females. So, we can say that this is number Cf divided by number f, which we can rewrite by n Cf divided by n into n by nf, and that is just the probability of. So, n Cf divided by n is just the probability of C intersection f divided by probability of f. Okay. So, that would be the probability that a randomly chosen person is color blind given that a female has been chosen. So, the general definition would be something like this. So, we could condition on any possible event, but the event on which we are conditioning, in this case the event that the randomly chosen person is a female, that should be an event of non-zero probability. So, given an event A of non-zero probability, the conditional probability of the event B given A, written as probability of B given A, is equal to, this is defined as probability of B intersection A by probability of A. Okay. So, we can take a sample space, a probability space, and based on a particular event, say A, we can define conditional probabilities. Okay. So, if this was your complete sample space and A was a particular event in it, now we are having a new probability space where the universe is just A, and all the events that are there in this is essentially obtained by taking its intersection with A. So, these would be the new events, and each of those events, they will have a conditional probability as given by this particular formula. Note that probability of B given A may not be equal to A given B, okay, because here the conditioning is based on A, here the condition is based on B. So, we can write this formula, probability B given A is equal to probability B intersection A by probability A as probability of B intersection A is equal to probability B given A into probability A. So, this can be thought of as a multiplicative form of this particular formula. Okay. So, this is a very useful formula if we are to compute the probability of an intersection. Okay. So, the probability of A intersection B can be computed as probability of B given A multiplied by probability of A, and this can be generalized as if you had A intersection B intersection C, this probability is equal to probability of say A given B intersection C into probability of B intersection C, which can again be written as B given C into probability of C. So, it can be thought of as a chain rule. Okay. So, if you had the intersection of many events, conditional probability can be used to determine the probability of the intersection. Conditional probabilities are often easier to find if you set up the sample space appropriately. We will see one famous rule called Bayes rule. So, now let us describe a sample space. So, this is a sample space and it is formed by many different events. Okay. So, these events form a partition of the sample space. Let us call that as A1, A2, A3 up to AN. So, we have a sample space which has been partitioned by events A1 to AN. When it is partitioned, these events do not have any intersection between them. AI intersection AJ is empty for each of these events. Now, if we were given a particular event A, this is even drawn in red color. Now, that event's probability, how do we determine? Clearly, the event A is equal to the union of A intersection AIs. So, A intersection A1 union A intersection A2, so on, that union would give us A. So, probability of A, the rules of axioms of probability, we can say that is just the summation of probabilities of A intersection AI, I going from 1 to n. And to compute the probability of this intersection, we can use conditional probability, and that would be probability of A given AI times probability of AI. Now, what Bayes' rule tells us is, suppose we are told that the event A has occurred. Okay. What is the probability that AI has occurred? So, we want to compute probability of AI given A. Okay. So, this can be thought of as probability of AI intersection A divided by probability of A, and probability of A we can use this formula, and for probability of AI intersection A we can write it as probability of A given AI into probability of AI, and the denominator is summation I going from 1 to n probability of A given AI into probability of AI. So, this rule is called as the Bayes rule. So, we are interested in probability of one of these AIs happening given that A has happened, that can be expressed in this particular format. Let us do an example involving conditional probabilities. So, let us look at a family with 2 children, okay, and we are interested in the gender of the children. So, there are 4 possibilities. The first child could be a boy and the second child also could be a boy. Okay, we are looking at the case where there are precisely 2 genders, basically boys and girls. So, BB is a possibility, BG is a possibility, which means the first child is a boy and the second child is a girl, and GB is a possibility and GG is a possibility. Okay. So, our sample space would consist of these 4 outcomes. If you look at one particular family, they will be in one of these 4 classes, and we can assume that all of them will occur with 1/4 probability. Assuming that boys and girls are equally likely in any pregnancy, we could say that boy happens with 1/4 probability, boy girl happens with 1/4, girl boy happens with 1/4, and girl happens with 1/4. Now, here is a question. Suppose somebody tells that a particular family, that a randomly chosen family has a boy. We are interested in computing the probability that it is a family with 2 boys. Okay. So, we are not told whether it is the first child which is a boy or the second child which is a boy, we are just told that the family has a boy. it could be that there is precisely one boy, it could be that both children are boys. Okay. And we are interested in computing the probability that the family is of type BB, which means both children are boys, given that there is at least a boy in the family. Think about it for a minute, you can pause the video and think it, and then we will work out the answer and see what it is. So, let us identify our events. Okay. Our event A is the event on which we are conditioning is the event consisting of BB, BG, GB. In other words, this means the family has a boy child, and the event we are interested in is, let us call it as C, that would be just BB. Okay. Both children are boys. So, we are interested in probability of C given A, and by definition this is equal to probability of C intersection A divided by probability of A. C intersection A happens with 1/4 probability, and A happens with 3/4 probability, because all of these three outcomes are disjoint outcomes, they happen with 1/4 probability each, add up to 3/4. So, this is 1/3. Okay. So, if you are told that the family has a boy, the other possibility, although there are only two possibilities, namely the other child is either a boy or a girl, but still the answer is not 1/2 as some of you might have thought, it is 1/3. Now, what is an intuitive explanation for this? So, suppose we had 1000 families. Okay. So, these 1000 families were chosen from our sample space, and each of these family could either be a BB family or a BG family or a GB family or a GG family. So, we can assume that 250 of them would be boys type, 250 would be boy girl type, and 250 would be girl boy type, and 250, the remaining 250 would be girl type. When you focus your attention on families which contains a boy, I mean at least a boy, those are essentially 750 families. Out of these 750 families, 250 of them are boy type, and 500 consist of one boy plus one girl. Okay. And so, you would expect the ratio to be 1/3, and that is what precisely this calculation shows us. Okay. So, this is a brief introduction to conditional probability. The next thing that we will see is something called as conditional expectation. So, just like conditional probability was probability based on a condition, conditional expectation is essentially expectation based on a condition. There are two distinct notions which goes by the name conditional expectation. We will see both of them in different areas. When people say conditional expectation, they might mean either of these notions, they are related, but they are not the same. Okay. So, let us see the first notion of conditional expectation. So, expectation is always with respect to a random variable. So, let us say you have a random variable and it has a certain underlying distribution, then we have its expectation. Expectation of y is just nothing but summation over all the values that y can take, y into probability that the random variable takes the value y. Okay. This is the expectation. We change this probability to a conditional probability, and what we get is called as conditional expectation. So, we have an event. So, condition the random variable on an event and recompute the expectation. That is an informal definition. This would be the conditional expectation. So, more formally, expectation of y is a random variable given an event A. So, here A is an event, this is equal to sum over all y's, y into probability that the random variable y takes the value y given the event A has occurred. Okay. So, this is the conditional expectation. Of y given A. So, let us look at an example. If you roll a die, okay, let us say the values that can come are 1, 2, 3 up to 6, all with probability 1 by 6. The expectation, so let us look at the outcome, we will call it as y. So, y is the outcome and y can take all these values 1 to 6 with equal probability. The expectation of y would be 1 plus 2 plus up to 6 by 6, that is going to be 6 into 7 by 2 into 6, that is 3.5. This is the expectation of the random variable. Now, if I say the event A has occurred, and A being that the roll results in an even number. Okay. So, you are told that the result is an even number. Now, what is the probability? You have to recompute the probabilities and weigh it accordingly when you do the summation. So, the conditional expectation of y given this event A is equal to, well, there are 3 even numbers that could appear, 2, 4 and 6, and all of them being equally likely. Okay, if you add them up, you will get 12 by 3, that is going to be equal to 4. Of course, if you condition on A complement, you will get, let us say 3. Okay. Expectation of y given another event A complement, that is going to be 1 into 1 by 3 plus 3 into 1 by 3 plus 5 into 1 by 3. That is 9 by 3, that is going to be equal to 3. You can see that even and odd are equally likely, and these conditional expectations when averaged out over the probability of the events, you will get 3.5, which is the expectation of the unconditioned random variable. When we talk about conditional expectation, the event is often described in terms of a random variable. Okay. So, the form that we will be most commonly using is the conditional expectation of y given the random variable z takes a value small z. Okay. So, instead of talking about an arbitrary event, we are looking at events which are described using, say, random variables. Okay. So, this is equal to summation over y into probability that y equals y given the random variable z takes the value z. Okay. So, this conditional expectation, this is going to be a fixed number. Okay. Both of them, if you condition on an event based on a random variable, they are all going to be fixed numbers. Let us do one more example. So, suppose we roll 2 dies. Okay. So, let x denote the sum of the values returned while throwing two unbiased die. Okay. X1, let us say that this is the value on the first die and x2 is the value on the second die. The random variable x, its expectation is clearly going to be expectation of x1 plus expectation of x2. Linearity says that this is going to be 3.5 plus 3.5, that is going to be 7. We could look at, say, conditional expectation x given x1 equals 3. By definition, this is going to be sum over all values that capital X can take, let us denote it by x, times the probability, the conditional probability that x is equal to x given x1 equals 3. If x1 equals 3, then the sum can range from, let us say, 4. So, 3 plus 1 to 3 plus 6, from 4 to 9, these are the likely value. All the other values happen with 0 probability. So, this is going to be equal to 4 into 1 by 6 plus 5 into 1 by 6 plus 9 into 1 by 6. That is going to be 3 plus 1 into 1 by 6 plus 2 into 1 by 6 plus 6 into 1 by 6. That is going to be 6.5. So, the conditional expectation of x given x1 equals 3 will be equal to 6.5. The second notion of conditional expectation, although it is called as conditional expectation, the notation is slightly different. So, we will write expectation of x given y. Here x is going to be a random variable and y is also going to be a random variable. In the earlier case, x was a random variable, whereas y, the second parameter, was an event. That event could have been described either as an event or by means of a random variable taking a particular value, but here it is just a random variable, okay. And therefore, this value is not in some sense fully determined. So, in this notation, when we write conditional expectation of x given y, what we mean is a random variable whose value depends on the value taken by y, okay. So, this conditional expectation is a random variable, whereas the other conditional expectation E of x given y equals y, this was a fixed number. In all cases, the context will make it clear whether we are using this notion or this notion. In this course, we will essentially be using only the fixed number notion, but it is good to know what is the random variable corresponding to conditional expectation. So, here this is a random variable and the values. So, we can think of the sample space for this random variable as the values that y can take, okay. So, let us view this as a function g of small y. So, g on small y, its value is equal to expectation of x given y equals y, okay. So, as the value of the random variable changes, the conditional expectation takes different values. By describing certain properties of conditional expectation, with respect to usual expectation, we had the linearity property, which says expectation of x1 plus x2 is, or cx1 plus dx2 is equal to c times expectation of x1 plus d times expectation of x2, or more generally expectation of a summation alpha I xi is going to be equal to summation alpha I expectation xi. Okay. So, this is the linearity property of expectation. One can show that this holds for conditional expectation as well, and for both the notion, whether you treat it as a random variable or as a fixed number. So, the conditional expectation of x1 plus x2 so on given an event A is same as summation expectation of, so over I expectation of xi given A. Okay, if you had constants say alpha 1, alpha 2, you could have alpha I here as well. Okay. So, this is basically the linearity of conditional expectations.